In this video, let's talk about hydrostatic pressure, or the pressure that you feel by being submerged in a fluid. So in the experiment you did in class, you were to determine how three variables affected the hydrostatic pressure, or the pressure at a depth in the fluid. One was how the fluid density affects the pressure. One was how the gravity field constant affects the pressure. And one was how the depth in the fluid affects the pressure. Now, in your results, you should have seen something similar to this, that the gravity field constant was proportional, or the pressure was proportional to the gravity field constant. Pressure was also proportional to the depth in the fluid. I'm going to call that delta H. And the pressure is also proportional to the density of the fluid. Now, we know when we do experiments where we're testing how multiple variables affect one variable, we test them each separately, holding the other ones constant, but we can combine our results by just multiplying the proportionalities together, and we can get an overall relationship that says the pressure is proportional to the, I'm going to write it just a little bit differently, or the way you might see it, rho g delta H. And really I should put a delta here because it's really the change in pressure is proportional to that. Technically, either way is fine for now. So that's the kind of results you saw, that it seems to be linearly proportional to these three different things. Now, a couple of things to notice. They're all linear, which is nice for us. And two of them seem to have y-intercepts, while one seems to go through 0. We'll get back to that a little bit later, why that might be. So what we're going to now is try to use our ideas of physics to theoretically try to kind of see if we can find the same equation using his physics ideas, and to give meaning to the results we got from our experiment. So we're going to do that by looking at our friend Pikachu here. Pikachu is at a depth in the water. We're going to look at the top of his head. So let's call the distance from the surface of the water to the top of his head, let's call that delta H. Let's make a couple assumptions. Let's assume that this is open to the air, so we'll call this PA. Again, A is really just talking about point A, but it's the whole surface is at the same pressure. Let's call the top of his head point B, just so we can talk about it. And let's say this fluid has a density of rho. Now we're going to do one more thing to make our life a little bit easier. We're going to assume Pikachu is a cylinder. So I'm going to redraw this. And so Pikachu is this green or yellow cylinder down here. This blue liquid is just a liquid that's below Pikachu, or below Pikachu's head. This is our point B. So this is the top. So this B is at the top of Pikachu. This green liquid is all the liquid that's above Pikachu. And this magenta cylinder is all the liquid kind of right here that's directly above Pikachu's head, which means the top of this green is our point A. And this would be our PA is up there. And it's the same fluid, so this is also density rho. Now we're going to try to write we want to find the pressure at point B. Let's try to write it using physics ideas. So if we say the pressure at point B, it's going to be equal to, now, we're thinking about what's pushing down on Pikachu's head here at point B. We have all this air pressure up here is pushing down on everything. So we're going to have the pressure due to that up there, because that pushes on everything below it. And we also have this magenta column. The weight of the magenta column is pushing down, well, at least a force the size of the weight, because as long as nothing is accelerating in here, we're going to have, if we, for example, had a book on a table, we would say, oh, the weight of the book is pushing down, the normal force from the table is pushing up. Well, that normal force from the table is pushing on the book. Well, the book is also pushing back on the table with a force equal to that. And the normal forces end up being equal to the weight in that case. So the same, again, we're going through a little Newton's laws process, but the size of this force ends up equaling the weight of so let's just call it W for weight for now, the weight of the magenta, fluid. Now I'm writing pressures, so I want to write this, go back to our idea that pressure was force per area. So I want to write this as the weight, but I want to divide it by this area up here on top of that to write it as I write it as a pressure. That's a good start. Now we also remember that sometimes it's more useful to write, when we're talking about fluids, to write weights in terms of densities. So the weight of this magenta part is going to be the density of the liquid times the volume of the liquid times G. And also I'm going to just add in here that for a cylinder, the volume of a cylinder is equal to the area of the cylinder times the height of the cylinder. Now, if I sub these back in here, we're going to see something nice happens, that the pressure at point B is going to be the pressure at point A, plus now this whole top thing becomes density of the liquid, area. Now, in my picture, the height of this magenta cylinder is our delta H that we're looking for. So I'm going to throw that in there, divided by A, because it's a pressure. And if we look at these areas, if you look at them, they're the same. This is the area of the cylinder. Well, this area is also the area of the cylinder. So these are going to cancel out. And we get our kind of final form of our equation that says the pressure at point B is going to be equal to the pressure at point A plus the density of the liquid times the, I forgot our gravity field constant up there, times the gravity field constant times, now in this case, all that's left is delta H, where delta H is the height of that cylinder, or in our case, is really the depth of our liquid, because the cylinder is from our surface down to Pikachu's head. And here we have our hydrostatic pressure equation. And we look at this, there's a couple nice things. This gives us the point, so this here we're going to call the absolute pressure. And this is the pressure at any point. I just happen to call it point B. This PA is usually our known pressure. And often it's going to be atmospheric pressure, because something's going to be open to the air environment. But that's kind of our known pressure. And this last piece here is really the difference in pressures, a delta P. And the kind of fancy term for it is the gauge pressure. And this tells us, though, that our pressure at point B, all it depends on is the pressure at some known point. And if we assume our liquid and our planets are constant, where rho and G are just constants, all it really cares about is, or all it really matters, depends on, is the pressure at some known point plus the depth. Now, just remember, this is a depth. So down ends up being positive. All it depends on is the pressure at a known point plus a depth. Now, why is this called the gauge pressure? Well, it's called a gauge pressure because, honestly, it's the pressure that a gauge measures. Now, a gauge is something that you might have experience with. It measures how much air is in your bicycle tires or your basketball. And what a gauge measures, it doesn't measure the absolute pressure inside something. It measures how different that pressure is from the air environment that you're in. So, for example, if you stick a knife in your bike tire and you pop your bike tire and it deflates, and you might say, oh, there's no air in there. Well, there actually is still air pressure. The atmospheric pressure is still inside there. When you pump it up, you're putting more pressure than the atmospheric pressure inside of it. Now, if you put your gauge on it, though, it doesn't take into account the atmospheric pressure. It just measures how much added pressure you put into it. It just measures this delta P part of the pressure. So our result's kind of a little bit cleaner. Now, again, the subscripts here really depends on whatever works for you. I just use A and B. Here I use 2 and 1. On your equation sheets or in a textbook, you might see it written this way, where the absolute pressure is just P. The known pressure is P naught. And they don't use a delta for the H. They say, just H is just the depth. I like the delta because it reminds me it's a difference in height. And also, if you're looking for the gauge pressure, remember, it's just the rho G delta H bar. And the other thing notice is to remember, this only depends on depth. It doesn't depend on what's directly above you. It depends on your depth with some known levels. So if there are other things, there's like a rock above your head in the water, your pressure doesn't care about that. Your pressure only cares about some known pressure level and how deep you are in that liquid. So for example, if you were measuring the pressure down here and you move, so right now this is open to the environment above us. If I move to the left, the pressure doesn't change, even though there's now something else above me, because this is not at the same pressure as is up here. It doesn't matter what's above me. I'm measuring that depth based on my known pressure level, not based on what's the first thing that's above me. If I move over here, pressure stays the same. If I go through this little tunnel, pressure stays the same. Go over here, pressure stays the same. It only changes if I start going to a different depth. Now, one last thing is, what about those y-intercepts? So why do these two have y-intercepts and the gravity field constant does not. Well, if we go back to our simulation for a second, if I'm at this surface right here and I start dropping, or I make my depth 0, for example, if I'm at some depth and I go up and up and up and I eventually make it 0 based on the surface, there still is air here. So there still is going to be an absolute pressure. There still is an air pressure up there. There is no pressure due to depth anymore, but there is still some pressure unless there's no air here at all. So I'm going to have, at least in this experiment, I'm going to have a y-intercept. Now, if I got rid of all the air up here, for example, if I was to, I think there's if I turn off the atmosphere, if I'm out in like deep space or something like that, now my pressure would actually go to 0. My graph would not have a y-intercept because there is no pressure. But in our experiment, we had an atmosphere, so that was the y-intercept. And the same thing with our fluid. If I'm in a fluid and I drop it, I can't do it here. If I drop the density to 0, it basically just takes all the liquid out and the air is going to fill in that space, and I'm going to be at air pressure again, or atmospheric pressure again. So even if I get rid of all a fluid going to 0 density really means it just isn't there anymore. If the fluid is gone, I'm still in an atmosphere though, so that I'm still going to have an atmospheric pressure. Now the weird thing though is if I am up here, let's say, and I drop gravity, so if I change density, it doesn't affect the atmosphere. And changing my fluid depth it doesn't affect the atmosphere because I'm in the fluid. But changing gravity does. Changing gravity affects everything. As you can see, if I drop gravity down, it also drops the atmospheric pressure and changes that. So changing gravity affects everything. So making gravity go to 0 is going to make not just my pressure based on depth, but my absolute pressure and my atmospheric pressure all going to drop to 0 as well. So that's going to have a y-intercept of 0. So again, in the end, what we really care about here is our hydrostatic pressure equation. Pressure is due to depth, and that we can write it, if we can talk about it in terms of gauge pressure or in terms of absolute pressure.